Okay, so I'm continuing on right where we left off, where I told you that we were going to work on Z2 to the n. So this is a vector field over the finite, vector space over the finite field Z2. And I already knew that I was working on the space. And what you can find quickly is that the map has periodic orbits. So I'm talking the language of dynamics that we had in class. For example, if I have n equals 3 and I iterate once under the Ducci map, I have 0 minus 1 is 1, 1 minus 1 is 0, and 1 minus 0 is 1. So I get 1, 0, 1. Iterate number 2 gives me 1, 1, 0. And iterate number 3 gave me right back to my initial condition, 0, 1, 1. So I have a period 3 orbit. It's a period 3 vector. So what I asked Maggie and Dennis, my two poor undergrads, is to put these zeros and ones in strings of length n and record what the periods were as a function of n, and hopefully we can actually find a pattern of what those periods are going to look like. So actually, I wanted to show you what these periods are. So for example, these are the periods that you get, and you do see patterns. Take a look at this for a few minutes and see if you can look for patterns. Like, for example, you see here that for 2 to the k, any power of 2, the string length, or the vector length in this case, the cycle lengths are going to all be 1 because everything's going to converge to the vector 0, and it's a fixed point. So you really only have a fixed point, which is period 1. Unfortunately, what happened, there's a couple things that happened. First, Dennis was probably the best at finding these periods, and he only found what we call the maximal period length. So if you look at the number of initial conditions you have, for n equals 3, the number of initial conditions you have are going to be 2 cubed, 8 different initial conditions to iterate. And that's because if you took probability, you know that you're taking 2 things in 3 different spots. So you have, by the multiplicative rule, 2 to the 3 choices. So he could literally iterate every single initial condition back for n equals 3. N equals 7, you're going to have 2 to the 7 possibilities. So you're not sure, but it looks like he didn't iterate every possibility, but most of them converged to the maximal cycle length, which was 7 in this case. N equals 15 was outrageous. You have 2 to the 15th possibilities of initial conditions. So what happened is he'd only find 15. So they were starting to look for patterns for what we call the maximal cycle length, but we weren't sure that there were actual sub-maximal lengths. We did find for n equals 6 that this submaximal cycle length of length 3 by just iteration on Excel. But capturing all of these was impossible, and he really didn't. He only got the maximal cycle length in his table. So the question is, how did I get all these other cycle lengths without Dennis? And the way I got that is by thinking about the map algebraically. You really do have to think differently about this map. You can't do what I suggested doing, which is putting everything into Excel and iterating it. So the first thing to observe is that subtraction on Z2 is the same thing as addition. 1 minus 1 is 0, and 1 plus 1 is 0, the same thing. Likewise, 1 minus 0 is 1, and 1 plus 0 is 1. And so the absolute values that I had here before, I don't need. I can actually just add instead. And that's pretty cool. Adding mod 2, I'm adding the even integers with the even integers business that I showed you the other day. So this vector, now this map becomes linear. It's a linear map. It wasn't on Z. On Z, it was not a linear map. The absolute value is definitely not a linear map on Z, but it is a linear map on Z2 to the n. And linear maps, if you remember from linear algebra, the most important theorem from linear algebra is that all linear transformations have a matrix representation. And when you get that theorem in a linear algebra class, you don't realize how important it is, but it's super, super important. And this map here now can be represented by this matrix. Just look and see. If I take an arbitrary vector here, x1 through xn, x1 plus x2 is the first component, x2 plus x3 is the second, and so forth, and I get x1 plus xn is the last component. So this is the matrix representation of the Ducci map on Z2 to the n. What's also cool about this is that it can be represented as the sum of two linear maps that I know a lot about. The first one is the identity. See the identity here? If I have ones down the diagonal and zeros everywhere else, I get the identity. And it's offset by this one on the upper diagonal and this one down here. That's a left shift map. So we're shifting everything to the left. And so this is really I plus SL to the I plus SL. It can be represented that way. So now what's good about that? If you look at the proof that n is equal to 2 to the k results in everything converging in finite time to a fixed point, the zero vector, that proof by Ann Ludington and that proof by Amos Ehrlich were fairly, at least a page long. I'm going to give you a one-liner made big. I just made this big in font. So if I have I plus SL to 2 to the k, well, I'm working on Z2. So that means all the inner terms by the binomial theorem are going to have even coefficients, and even is 0. So all the inner terms drop out. We used to joke around that in Math 100 type classes, that type of algebra is standard. So all those inner terms drop out, and I'm left with just the first and the last term. But if I shift left n times, then I'm back to where I started. So SL to the n power is really I. And that's really 2I. But 2 is 0. So it's really 0I, which is 0. So in one line with three equations, I've shown that this is equal to 0. It's beautiful. So those patterns did come from a theorem. I had to use algebra to find these other periods. So I recast this thing. So let me show you what that looks like. Suppose that I have, first you need a definition. Then actually I'm going to stop this module and start again. So up to this point, in the next module, I'm going to show you where I got these periods from using algebra. And in algebra, there's two things. If I had to describe algebra in as few words as possible, I would use the word polynomial. And the second set of words I would use is solving equations. That's what algebra is all about. Abstract algebra is about that. Real analysis, taking limits. Abstract algebra, polynomials, and solving equations.